In this example, we are going to, well, read what this example is about and then solve it. So first of all, it says assume that t is linear, or in other words, it's a linear transform. And then, given that assumption, find the standard matrix A such that t of x is equal to ax. Well, that on its own isn't enough. It's like, well, I need to know something about this linear transform if I'm going to find the matrix that goes here. Well, they tell us some more. First of all, the transform is going to go from 2 space to 2 space, R2 to R2. And it first reflects through the horizontal x1 axis and then through the vertical x2 axis. Well, regardless of how you label these, x1, x2, xy, whatever, it's the horizontal axis and then the vertical axis. So first of all, I will use their labeling of x2 for vertical and x1 for horizontal. And what I'm going to do is I'm going to put down the standard basis vectors. So first of all, I'm going to have, and we usually use E to represent those. So E1 is the vector 1, 0. It's 1 in the x1 direction and none in the x2 direction. And we also have the standard basis vector E2, which is 0, 1. None in the x1 direction, but 1 in the x2 direction. And so one technique for finding out the standard matrix is, first of all, just take your standard basis vectors and transform those individually. When you're done, you can just throw those into a matrix and you'll have your standard matrix. So what I'll do is first, I'm going to reflect through the x1 axis. So if I'm reflecting through the horizontal x1 axis, first of all, if that means flipping this way, by the way, rotating like this. This isn't going to change because it's on the thing that's rotating. So when I'm done, E1 is not going to have moved. But E2 will. E2 is going to flip from here to here. And we can just geometrically figure out what that becomes. If I move this from here down here, it's still 0 units. I'm going to call this E2 prime because it's been changed. I'm not going to say it's the transform of E2 because notice we still have more things to do. So I won't call these the transforms of the basis vectors until I'm done. Well, E2 prime is going to be none in the x1 direction and now -1 in the x2 direction because it's going down instead of up. So now I've reflected through the horizontal x1 axis. That piece is done for. Well, now what I need to do is reflect through the vertical x2 axis, like that. Well, if I'm reflecting this way, notice the orange one doesn't change, it's just stuck there. But this one does. E1 goes over here. So again, just a reminder, I'm rotating this way. And so this moves over here. And so I have E2 prime, I'm sorry, E1 prime, because that's this vector, is -1, 0. It's -1 in the x1 direction and 0 in the y direction. Let me redraw those in isolation right quick. And now that I'm done, I can safely call these the transforms of E1 and E2. The transform of E1 is over here. And it is -1, 0. And the transform of E2 is down here. And it is 0, -1. Now what's cool about this is once you've determined those individually, well, your standard matrix, the way they write this formally, A is just the matrix whose columns are the transform of the first basis, the transform of the second basis, and if this was 3D space or higher, you would just keep going. So my standard matrix A is -1, 0, the transform of E1, 0, -1, the transform of E2. And so I can write my linear transform, T of any vector x, in R2 anyway, is equal to -1, 0, 0, -1 times x. So what does this transform do? Well, if I first reflect across the x1 axis and then across the x2 axis, can you also see that what has happened is that I've taken these and I have rotated them 80 degrees. So this takes any vector. Say there was a vector pointed over here. If I do the transform, let's say this is x. If I do the transform of x, this is going to rotate 180 degrees. So now it's going to be over here. And this would be the transform of x. So we've already found it, but there is another way you could do this. If you recognize that this is a 180-degree rotation, Well, then the matrix for a rotation, I'll call this A sub ROT for rotation, is always equal to this. It is cosine theta, sine theta, negative sine theta, cosine theta, which is pretty cool. So if you want to rotate any vectors, if the transform you want to do is a rotation, you can just figure out what angle you're rotating by and throw it in here, and you'll still get your standard matrix. Notice that if my rotation is 180 degrees, or in other words pi, well, cosine of 180 is negative 1, sine of 180 is 0, negative sine of 180 is still 0, and cosine of 180 is negative 1. And you can see that we have the same matrix either way. So whichever way you prefer to think of it, nonetheless, we now have that the explicit way to write down this linear transform is with this matrix right here. And the way most people first learn is to transform the standard basis vectors. But then you can also remember, oh, if it's a rotation, use this guy right here. And that is this example.